As a young group leader looking for a challenging project at the LMB in the late 1970s, John Walker got interested in ATP synthase, one of the key enzymes of oxidative and photophosphorylation. ATP synthase is a large multi-subunit complex found in the membranes of eubacteria, chloroplasts and mitochondria. And over the next 16 years, John and his lab determined the complete sequences of multiple ATP synthases from bovine heart mitochondria and eubacteria, culminating in the 1994 publication of an atomic resolution structure of the F1 ATPase, the catalytic domain of the enzyme, from bovine mitochondria. This work led to the realization that the energy released by oxidation of high-energy compounds in foodstuffs is coupled to the synthesis of ATP by a mechanical rotary mechanism, a new principle in enzyme function. With this beautiful work, John substantiated a theory presented in 1974 by Paul Boyer to explain how ATP synthase worked. And 3 years later, the two men won a half share of the 1997 Nobel Prize for Chemistry. Shortly thereafter, John left the LMB to become the founding director of the MRC Mitochondrial Biology Unit in Cambridge. He was knighted for services to molecular biology in 1999. John, thank you very much for coming to talk to us today.
It's a pleasure.
I want to start off with when you first came to the LMB. So you showed up here in 1974 on a rather precarious contract. Can you tell me a bit about that?
Yeah. At the time, I was working at the Pasteur Institute in Paris in what was called the Service de Chimie des Protéines, and I was quite happy there. And I seemed to be under consideration to becoming what was called a Pasteurien, which is a big deal. And around Easter 1974, I came here to an EMBO workshop, which was held in St. John's College, organised by Richard Perham, Ian Harris. And it was about how to sequence proteins by direct methods and other protein chemical aspects. And at the dinner, which was held in St. John's College, I found myself sitting next to this rather obscure little man. And he said, "Who are you?" And I told him, and I said, "Sorry, I don't know your name." He said, "I'm Fred Sanger." And I blurted out, "Oh, I thought you were dead." And he said, so I started scrambling then. And he said, "Why?" And I said something like, I wrote an answer in my finals at Oxford, which was described the reagents attributed to Perkin, Greenyard and Sanger, and I knew the other two were dead, so I assumed you were. And anyway, we got on quite well, and at the end of the evening, he said to me, "Have you ever thought of coming back to this country?" And I sort of thought, I think I just did. And at that time, we had a holiday home in South Wales and shared with a friend, and he urged me to get in contact with Fred on the way back to Paris. So I did, and I came here. I always remember the daffodils were out on the roundabout. It was mid-April. And after talking to me for a while, Fred said, "You can come here if you want. We don't have any money for your salary, but you can come if you want." So I had an EMBO fellowship, and they agreed that I could transfer it from Paris to Cambridge. So within a month, I was here, and there are 3 months of the fellowship left. And after I've been here for maybe 2 months, Fred came and said, "You seem to be okay, Walker. Why? We'll find money for another year." And so it went on. And then during that year, so I was now MRC funded. During that year, Fred said, "I think you should stay for a longer period of time." And it sort of went from there. So it was a rather precarious situation in a sense, but it clearly was a huge opportunity, and one that I didn't want to pass up. And of course, it was transformative in terms of my life and career.
You weren't bothered then that you might be out on your ear after 3 months?
Well, I mean, my wife and I talked about it, and we just decided we'd do it. And I wouldn't say I wasn't bothered. I realised there was huge risk involved. We didn't have children at the time, and decided to do it. The Pasteur was a big melting pot. I mean, it was a really interesting place full of all kinds of interesting people who you could access and talk to, preferably in French, but not necessarily so. And I was fortunate to meet Jacques Monod and talk to him. Francois Jacob was a little bit more reserved, actually, and not so easy. And then I arrived here, and I just sort of, wow, this. I mean, not just the people, but the sort of breadth and depth of what was going on. And coming to the LMB was an education in itself. And one of the things that I noticed very quickly was how social the place was, in the sense that people talked to each other a lot. They had coffee together and all of that stuff. And I thought, okay, this is the place for me. If I could stay here, I'll be very lucky and very happy.
So did the socialising extend to outside the lab as well then?
Yeah, it did, because the lab kind of became the central theme in my life anyway. So apart from working quite hard, we had soccer teams, field hockey teams, cricket teams, even darts teams. We used to play darts against other people. And then, of course, our children, once we had children, our children knew other children from other people in the LMB. They went to school together. They became friends, and so it was like being part of a big family. And once you begin to think about it, why is this place like it is? It became very clear, that this had been carefully thought through by the founding chairman, because Max was chairman, not director. And he'd set the style of the place. To
the extent that Gisela Perutz was in charge of the canteen.
Yeah, so you'd turn up in the canteen, and some days Gisela were there to greet you and ask you how you were and all this kind of thing. And she brought pieces of art from her home and put them up around the canteen, and it gave it a kind of family atmosphere. And then, of course, as we all know, everybody was on first name terms, and Max was Max, Fred was Fred. There was no professor this, professor that, doctor this. Those titles didn't exist. And the other thing that I think was very important in creating a unity for the place is that there were no divisions between academic staff and technical staff and support staff. Everybody was mixed up together. Everybody spoke to each other. We all had coffee together, and in these social activities of playing soccer and cricket, it was there were teams that included everybody, people drawn from all parts of the lab. And I think that made people feel, that it clearly was already a very successful place, and made them feel they were part of the success of the place. And indeed they were. The people in the workshop were really important for making pieces of equipment that didn't exist to our requirements, just to take one example. And so it was unique in that respect, I think.
So did the family atmosphere kind of dilute out the fact that intellectually it could be quite intimidating?
No, I don't think so. As I say, you could decide at coffee time who you went and spoke with. You might want to talk about cricket. You could go and pick out the right people. If if you wanted to talk to Max, you knew very well you better not start talking about cricket or soccer. You know, you had to talk about something intellectual, and he wouldn't, as it were, allow that kind of discussion in his presence. And so there were all kinds of conversations. You did what you selected for yourself, really, what you wanted.
Yeah. So you were working on something with Fred to begin with, were you, and then moved on to your own work?
Yeah. I was doing this protein sequencing. I mean, I wrote several papers about it, protein sequencing as an aid to rapid DNA sequencing. I mean, I've said it before, it really was the beginning of proteomics, before genomics. Genomics began with Fred and DNA sequencing, and proteomics was to do with interpretation of genomes, and it began in the LMB. I don't think they recognise that, actually. It's something that I should write about, really, just
you should
convince the world about it.
You definitely should. And did you feel that there was some sort of pressure to do something brilliant? I mean, you knew that you were amongst brilliant people, and I could have survived in a sort of more routine kind of role. I could have run the protein sequencing activities in the LMB, and that was discussed. But I wasn't interested in doing that at all, and I told Fred that at the time. And so I was doing these experiments with Fred, but I was actually officially working with Jan Harris. And Jan was interested in thermophilic proteins. And he'd originally had the idea that there was a new bond to be discovered beyond ionic, covalent, and hydrogen bonds, which would explain thermophilicity. This was an idea that was around, but it rapidly became clear from a physical chemist who worked with him called Bob Jack, that actually to thermostabilize a protein, you needed to put very few kilocalories into the structure of the protein in order to thermostabilize a protein by 5 or 10 degrees. It's just a matter of a few bonds here and there. So in a sense, it was trivial. But we worked on thermophilic enzymes in collaboration with people in structural studies who were doing the structures of glyceraldehyde 3-phosphate dehydrogenase, and then Phil Evans did phosphofructokinase. And so I was working on that as well. And then, very unfortunately, I think it was 1978, Jan was killed in his holiday home, and that kind of, as it were, opened up an opportunity for me. And so that was the point at which I had the opportunity to have, to think about having a research activity of my own. And so by this stage, Fred had got finished with Phi-X and G4, the related phage. And it's extraordinary, actually. He read an article in Tibbs which summarized the sizes of DNA molecules. So these phages, 5-6 kilobases. It's amazing when you think it took 10 people 2 years to sequence 6 kilobases. So there was a table in this article. The next one down, next biggest one was human mitochondrial DNA, 16.5 kilobases. Okay, we'll do that one next, three times bigger. And so he came to me, he said, Walker, you're a biochemist, make some mitochondria and some mitochondrial DNA. So I rapidly did a lot of reading, and the upshot was that we made human mitochondria from placentas that I got from Mill Road maternity home. And the full-term placentas were very difficult to deal with physically. They had a lot of connective tissue. And so I hit on the idea of getting caesarean placentas. And that turned out to be a really good idea because they were
easier to work with, and actually they came at a specific time in the afternoon.
Yes, I was thinking, were you having to go there in the middle of the night?
It did transform things, and with another Australian, Ian, we made human mitochondrial DNA, and that's what was sequenced. And then, of course, the sequence came along. I had the same job. Okay, we've got these 13 proteins encoded. They're all hydrophobic. What are they, John? Well, 2 of them you could recognize because there were bits of sequence for cytochrome B, and I think it was cytochrome oxidase 3. And so I started making proteins from mitochondria. So there's a way in which you could specifically radioactively label the 13 proteins and get a gel with the 13 radioactive bands in it. So I started sequencing them. But the problem was that all the proteins were formulated on their amino terminus, so you couldn't do Edmond degradation on. So I then started trying to remove the formal group by treating the proteins with mild acid, which was an approved way of doing that, but some proteins will get degraded. So it was really touch and go stuff. But I managed to identify 3 of the proteins, COX-1, ATPase6 and ATPase8. And then Fred wrote his paper and he quoted those results without asking me, without putting my name on the paper, which, was kind of the way people might behave in those days. He wanted a paper about DNA sequencing. I didn't complain about it. I just thought, okay, that's the way it is. But people don't realise actually that I did identify those. Anyway, it doesn't matter. So I became interested then in the 13 proteins. What are they? And eventually it became clear they're all components of the enzymes in oxidative phosphorylation. And I started going to meetings, actually, that were about mitochondria. Fred got invitations when the mitochondrial DNA sequence, and he didn't want to go to the meetings, and nor did any other members of his group. So Fred sent me along, and I actually talked about the mitochondrial DNA sequence in these mitochondria meetings in Italy and elsewhere, and got to know this kind of community. And I realized that there were opportunities for people like me who knew quite a lot now about how to determine sequences and of proteins, and realized that almost nothing had been done in this entire area. So I looked at the respiratory enzymes and I thought, well, which is the most interesting? And I eventually picked the ATPase, having done a lot of reading.
Why had nothing been done?
They were focused on, the whole field had been focused on this huge controversy about what was the intermediate in energy conversion. So there were 2 camps. There was the camp that said there was a high energy bond at the form of thioester or something of that nature. So that was the squiggle camp. And then there was Peter Mitchell with chemiosmosis, and Mitchell was very embattled, and he sort of had the whole world against him. But of course, in the end, he was right. But that polarized the whole field. That's all they thought about. That's all they talked about at these meetings. And so I think that held the field back, in terms. And then there were difficult enzymes. The membrane bound, some membrane proteins was a big deal. Hardly any membrane proteins have been studied. And before I got into this, actually, there were people in the lab, Mark Bretcher, Richard Henderson, were encouraging me to work on membrane proteins. So I worked on bacteriorhodopsin for a while, and then I hit on the ATPase.
Just because they were complicated technical challenges, or?
They're very difficult technical challenges, and the people in the field showing you, they hadn't even worked out how to purify the enzymes the whole enzyme complex. They'd worked out how to make bits, but not the whole thing. So there are all kinds of basic biochemistry that had to be put in place in order to make the field approach. I wasn't the only one doing this, but I was certainly in the lead in terms of the ATPase, and later on with another bigger enzyme. It's got 45 proteins in it called complex 1, which is the entry point for electrons into the electron transport chain. So I think that was why it was held back, was because of this dispute with Mitchell and the rest of the world. And
being here with the sort of the viewpoint of the LMB gave you a bit of an edge on the rest of the field.
That's right. And so, the idea that I was taking on something big and possibly important, I think that was in its favour, really.
Before we move on to that, I just want to ask you, first of all, what Fred was interested in, if he wasn't interested in this fascinating problem.
Fred was interested in sequences. Yeah. And of course he wrote this review in annual reviews, sequences, and sequences. That was his sort of swan song when he retired. That's what he was interested in. And I once had an amusing conversation with Sidney, who said, he asked me, had I noticed the rule of 3? And I said, you mean mitochondrial DNA is 3 times bigger than phi X, and lambda is 3 times bigger than mitochondrial DNA. And he said, yes, that's the way Fred operated. He went up in steps of 3, and that's what he did. And so after mitochondrial DNA came lambda, phage lambda, and by that stage, the people working with Fred who'd made these earlier projects work, because he couldn't do it all on his own, they were beginning to form their own ideas of what they wanted to do, and they sort of didn't want to help Fred finish lambda off, and he was quite frustrated, because he wanted to finish it off. But fortunately, there was a New Zealand sabbatical visitor who did help him finish it off, two New Zealand sabbatical visitors. And so he was interested in sequences. And but he definitely saw a role for protein chemistry that many other people did not. And I can remember people being in the lab being quite negative about protein. Who the hell wants to do direct protein sequencing? Once the DNA sequencing methods became established, but it's quite clear they're complementary, and of course they remain complementary. So, in a sense, Fred was quite visionary, far-seeing in that respect. But he wasn't interested in how enzymes work or structures of proteins, or he may have been interested in a general sense, but you'd never get a conversation with him about anything of that nature.
And I think you've said in the past that he didn't say a lot, but he was quite perceptive.
He didn't say a lot, but when he did say something, it could be very, very penetrating and even devastating, because as he became closer to Fred, he became quite paternalistic, and he'd rap you over the knuckles. Whereas if you clearly weren't staying around for very, very long, well, he didn't care. But anybody that he cared about, he would be critical, actually, and sometimes he could be quite hurtful. Things that he would say to you in private, as it was kind of mentoring you in a sense. It was very rare, that Fred would say something, but when he said something, it meant something. There was no tittle-tattle, there was no small talk, it was to the point.
Yeah. What did he think of your F1 ATPase idea then?
He was delighted.
Why?
So when I told him I was going to work on ATPase, he just said, well, get on with it. Don't waste my time until you got something to show me. But to me that was a green light just to get on with it. I got his support, and I could get on with it. And that.
What do you think it was that he liked about the project then?
I think because it was seemingly impossible. It was on the cusp of what was possible, and people forget this. But first of all, it took from 1981 to about 10 years to actually grow appropriate crystals of the catalytic part of ATPase. And we had crystals very early on, but they were mosaic. They didn't diffract appropriately, and it took a postdoc, René Lutter, and myself a very long time actually to sort all that out. And it was actually at the time, it sounds extraordinary, but it was the biggest structure that had ever been asymmetrical structure that had ever been determined at that point in the early 1990s.
So Fred liked the idea that it was technically challenging and...
Yes, yeah. Because I think, what it correctly foresaw is that if you take on challenging problems, you're probably going to have to invent new methods. And it's quite clear that inventing new methods and substantially improving existing methods has been all part and parcel of the success of the LMB, and it puts you ahead of other people immediately. And there are several points in that project, where we did that, where we invented vastly improved on methods.
Yeah. And I gather that there wasn't universal support for doing this project.
No, there were different opinions. So Cesar was becoming, he was joint head of the division with Fred, and Fred was going to retire, so I thought I should speak to Cesar. And Cesar had actually worked on enzymes in the biochemistry department with Fred a long time before, and clearly didn't like that part, and so he told me enzymes are boring, and and then Max was not so I went to talk to Max about it, and Max just looked looked me straight in the eye, and he said, "John, that's a life sentence." And I thought, ridiculous, I'll have this sorted out in 5 years. And of course he's absolutely right. We just finished, so we finally understood how the thing works last year. So, it's taken me 40 years to actually get to the bottom of it. And then Sidney just shouted obscenities at me. And
so he was the director at that point?
He was becoming director, yeah. Or maybe he was director. And who told you can work on this project? I'm the director. I said, well, Fred did. And then he stomped off. And the following day he came back with a little test tube. Here, there's something in here that you'll find very useful. Oh, what is it? It's a lambda phage, and it has the whole sequence of the E. coli operon in it. So that gave me a head start, actually, over many other people in this field. And Nick Gay actually played a big role in chopping out the appropriate part of the lambda, the piece of the E. coli genome that was in that particular phage, and cloning the fragments, and then we sequenced them, and that really made me arrive in that field. So I remember going to a Gordon conference and talking about this, and people were stunned that all of a sudden here is the sequence of all the subunits of a bacterial ATPase in one go, and there were more subunits than people expected, actually. And you could work out some of their properties, but they were very naive. They asked me things. Well, can you tell us how many subunits of each there are from looking at your DNA? So, no, I can't tell you that. I'll have to do some other experiments. And but it got us off to a flying start, actually, and it made a huge difference. Yeah. So Sydney was helpful.
So there wasn't a point then where you thought that what you were doing wasn't going to work and you should give up?
No, I mean, I felt quite confident, actually, and we were generating information all the time and publishing. So, we published a lot of work in good journals. And I wasn't just working on sequencing and characterizing the subunits, the ATPs. I was getting interested in other components in mitochondria, particularly the transport proteins. We made a big breakthrough there by identifying the biggest family of transport proteins we now know today that exists in mitochondria. And Matti Sarasta and I came up with what has proved to be the basic structure of these, and the fingerprint of these transporters. We came up with that in 1981, and it's a highly quoted paper, and that was just through bioinformatic analysis, which Andrew McLaughlin helped us with, actually. So we were doing other things, and I think we were doing interesting things. I managed to attract very good people to come and work with me, very good students, like I mentioned Nick and Victor Tibilevich, for example, Alison Cousins, and they were terrific students. And then I had very, very good postdocs like Matti and René Luther, and we had a really dynamic, active group of people.
And did you feel that at that point PNAC was extremely immunological? Did you feel like you were a bit on a limb compared to?
Yeah, I mean it was, of course. So Cesar had wanted to change the name of the division to the Division of Immunology, and I went and talked to him and said, I'm never going to become an immunologist, and I'm quite active and reasonably successful. And there's BART. And, BART is quite a big activity as a legacy from Fred, and so why don't you just leave the name as it is? And he was very gracious about it and agreed to do that. But, of course, the division was dominated by immunology, and the lectures, the internal seminars were largely on that. But I took it as an opportunity to learn about aspects of immunology. I didn't mind, and Cesar seemed to put up with me. He could see that I was doing, I was productive. And then when it became clear that I was actually doing something important, Cesar became a great supporter and fan. And
so when was that then?
Well, it would be in the 1990s.
So quite a long time after you started.
Quite a long time after, yeah. But he left me alone. I mean, he didn't try and, squeeze me for space, squeeze me for funds. I had a fair share of studentships and so forth. So there was never any suggestion that he was trying to squeeze me out because I wasn't one of them, as it were.
Yeah. Do you think you'd have been able to do this in other places that weren't core funded?
I think it would have been very difficult because, for many reasons, as we both know, if you're operating on 5-year program grants, you need to show a lot of information in advance that you've already done. Well, it wasn't like that. We could show some information, but I'm sure people would not have been convinced, that we were actually going to solve this problem. Mm-hmm. So I think having the stable funding of the LMB, and even when the 5-year review was, of course, we have 5-year reviews in the MRC. Even when they came around, I remember the chair of one of the committees saying to Fred, "He's going to get beaten, And Fred told me this after the event. And
that had already happened to you with bacteria rhodopsin, is that?
That did happen to me with bacteria. I got rolled over by 2 big groups. One was led by Ovchinnikov in Shemyakin Institute in Moscow, and the other one was led by Gobind Khurana at MIT.
Was this something that kept you awake at night then, that you were going to be scooped on the ATPase?
Not really. I mean, I didn't like being beaten.
No, but I mean in terms of the F1 ATPase, did you think that?
Not really. I mean, there was some competition from an American group, but I mean, they weren't committed to it in the same way as we were. That was my estimation. And but there's always a fear, you know, that you'd open Nature on Thursday and find the whole blooming thing sitting there after 12 years, and that would have been a disaster. So certainly as we got closer to writing the Nature paper on the structure of F1 ATPase, I did lose sleep, actually, that, you know, that it might appear before from somebody else that we didn't know about.
Was anybody else that close then?
No. No, there wasn't, no.
Why did it take so long to crystallise?
Well, it was this technical issue of getting the molecules to sit properly in the crystal lattice, so they would diffract X-rays appropriately, and this eventually René and I achieved. And I remember, we had this diffraction pattern, and I showed it to Aaron, and to seek his advice, and he said to me, "You need help," and he said, "You need a professional crystallographer to help you," and so he arranged for me to start collaborating with Andrew Leslie, and that was absolutely crucial. I mean, we couldn't have done it without Andrew. So it was to do with growing the crystals in an appropriate kind of way. And you have to remember, we started off from base 0. None of us had ever crystallized proteins before. And although there was expertise around, people didn't get involved. They would give some advice, but in general, René and I had to learn to do things ourselves by trial and error. And again, Fred helped actually, because we weren't in the structural studies division, we didn't have, as it were, untrammeled access to their facilities for growing crystals. So in the end, we built our own crystal growing room in PNAC. Thanks to Fred's support.
So have you got particular high points and low points that you remember of this enormous process?
I mean, I don't ever remember being depressed, or thinking, "Oh God, this is never going to work," or anything like that. I think I was always upbeat about it. I just thought we would find a way in the end.
Yeah. So 1994, you published your big paper, 2.8 angstrom resolution, and I think we have here an extremely molecularly accurate model. Is that the whole thing?
That is the whole thing, and what we. So you have to imagine that there's a biological membrane from the grey up to about here. And so everything below is buried in the membrane, all that lot's poking out. So we were solving the red and the orange bit with a little bit of the blue in the middle. That's what we did in 1994, and it's taken ever since then to get everything else into place and to work out how the whole thing works. But when we looked at the structure, what we wanted to do was to try and explain Paul Boyer's observations about what he called the binding change mechanism, and he had worked out that the energy requiring steps in ATP synthesis were in the interconversion of the catalytic sites through 3 different states that have been defined biochemically. And once we looked at the structure, I thought, there's only one way you can do this, and that's to turn this thing round in the middle.
So was that completely unprecedented at that point?
It was unprecedented. There was the flagella motor as a rotary machine, but that was a machine, not an enzyme. And so this was, an enzyme with a mechanical rotary mechanism bring about biochemical steps. And when I first talked about it, people would patronise me and tell me I didn't know what I was talking about.
Because you weren't a crystallographer.
No, because I wasn't an enzymologist, and enzymes don't work like that, John. But then, fortunately, some Japanese biophysicists did this beautiful rotational experiment where they couldn't have done it without knowledge of the structure. They had to know where everything was in order to attach the actin filament, which they could then see going round like an aeroplane propeller.
So this whole part of the structure rotates?
They took this part. No, it's just the bit in the middle, actually, the brown and the blue bit, and where it penetrates up here that rotates.
Oh, I see.
And all of this lot is actually providing the inlet for energy to make it rotate.
Uh-huh.
And this is a stator, which is holding that part and all that stuff there static relative to the rotor in the middle.
How did that feel when you realised how it was working?
Yeah, well, it was a kind of eureka moment.
That's even more exciting than when Max saw haemoglobin, I think.
Well, I don't know about that. But it was a very exciting moment. And then to see this validation of the idea was great, actually.
Yeah. And then everything started happening very quickly after that. So 3 years later, which is a really short time, you won the Nobel Prize. Was that a surprise that it was so short?
It was a huge surprise to me, except people started phoning me up and saying, "You're going to win the Nobel Prize." And I just said, "Go away, I don't want to talk about that." And on the day of the announcement of the prize, I actually went home and started working in the garden and missed the call from Stockholm. And at first I knew about it was...
So they phoned the lab, or they phoned your house?
They tried to phone me at home, I think, but I didn't hear it because I was up an apple tree. And then eventually I did hear the phone in the house ringing. So I went into the house, and it was a radio station in Cologne, and it said, "Mr. Walker, how does it feel like to win the Nobel Prize?" And I said, "I don't have the first idea." And they said, "Well, you've won it." And so then I contacted Stockholm, and they confirmed that I had. And then I...
Did you not have a telephone answering machine?
No, we didn't. No, very unsophisticated, and of course it was pre iPhones.
Yeah.
And so, having rung up my family, I then rang Fred up to tell him, and he said, "You deserve it."
So it's not worked out as too much of a terrible life sentence then, working on this?
No, I think it's been a great life, and I feel very privileged to have come here in the first place. As I say, meeting Fred totally transformed my life, really, which just would have been very different if if that chance encounter had not occurred. And I hope that I've made the best of it and contributed something useful.
I think we can agree that you have. John Walker, thank you so much for coming to talk to us today.
It's a great pleasure. Thank you very much.